Welcome. The new morning with a smile on your face, love in your heart, and good thoughts in your mind. And you'll have a wonderful day. Says Kate Sweat. Good morning, everyone, and welcome. It is with great pleasure that I extend a warm welcome to each one of you on behalf of New Prince Sri Bhavani College of Engineering and Technology to this faculty development program on the topic role of physics in the development of advanced materials. We are delighted to see a strong response around 150 participants who turned out for the program, which we believe will be a valuable experience for all of you. This FDP is designed to provide you with the latest insights, tools, and best practices in specific areas like bulk and nanocrystals, remote sensing, innovative engineering materials, water splitting, and how it bridges physics and technology and connects material science with engineering and science like seesaw. We have carefully curated a program that includes engaging sessions, which will be led by distinguished experts like Dr. Muthu Sendil Pandian, research scientist from SSN institutions, who will give a talk on physics for bulk and nanocrystals for technological applications, especially solar cells. And on the second day, Dr. Siva Madhusudan Acharyalu from Visakhapatnam will speak about physics of remote sensing. On the third day, we have an excellent speaker from Andhra Pradesh, Dr. M. Venkadeshwaralu, who is going to give a talk on the physics behind innovative engineering materials and technology. On the fourth day, we have an eminent speaker, Dr. Vijay Kumar Parandaman, postdoctoral fellowship from Malaysia, who will give insights about two-dimensional PT-like materials, bridging physics and technology for next-gen water splitting. On the final day of the program, we have another international speaker, Dr. Mangalaraja Ramalinga Vishwanathan from Chile, who will speak about material science, a seesaw of science and engineering. We understand that the role of a faculty member is constantly evolving, and we believe that continuous professional development is crucial for maintaining high standards of teaching and student learning. This FDP aims to equip you with the knowledge and skills necessary to enhance your teaching effectiveness, faster innovation in your classrooms, and ultimately contribute to the academic growth of our students. We are incredibly grateful to our resource person, Dr. Muthu Sendil Pandian, Dr. Shiva Madhusudan Acharyalu, Dr. M. Venkadeshwaralu, Dr. Vijay Kumar Parandaman, and Dr. Mangalaraja Ramalinga Vishwanathan for their willingness to share their expertise and experience with us. We also extend our sincere thanks to our chairman, vice chairman, director, our principal, head of the department, Dr. S. Sivagami, who motivated us to conduct this program, and thanks to the organizing committee, whose hard work made this program possible. We encourage you to actively participate and engage with your fellow participants and make the most of this opportunity to learn, collaborate, and grow. We hope this FDP will be a stimulating and rewarding experience for each of you. Thank you once again for joining us. We wish you a productive and enriching time at this FDP. Now I invite our head of the department, Dr. S. Sivagami, to felicitate our resource person and say a few words about our FDP. Ma'am, over to you, ma'am.
Yes, ma'am. Good morning, honorable present here. It gives me immense pleasure to extend my heartfelt felicitation to the organizer, dignitaries, resource person, and the participant of this 5-day faculty development program and role of physics in the
Now I invite Dr. E. Annie Ratnakumari, Assistant Professor at Department.
At the outset, I sincerely acknowledge the visionary leadership of our respected chairman, Thiru K. Loganathan, vice chairman, Thiru L. Naveen Prasad, and the valuable guidance of our director, A. Swaminathan, and the principal, Dr. T. Saravanan, who encouragement and support how this FDP possible. I also extend my heartfelt appreciation to the FDP coordinator, Dr. A. Annie Ratnakumari, co-coordinator, Dr. D. Beulah, organizing committee members, Dr. P. Jayachitra and Dr. B. Shiba for their dedication and meticulous planning in bringing together distinguished experts from India and abroad. We are truly honored to felicitate our eminent resource persons, Dr. Muthu Sendu Pandian, Research Scientist, SSN Institutes, Chennai, for enlightening us on the advanced application of physics in research. Welcome you, sir. Dr. Siva Madhusudanan Acharyalu, Associate Professor, Raghu Engineering College, Vaishak, for sharing his academic expertise and research insights. Dr. M. Venkateshwaralu, Assistant Professor, Konur Lakshmaya Education Foundation, Andhra Pradesh, for inspiring us with his scholarly contributions. Dr. Vijay Kumar Parandaman, Postdoctoral Fellow, University, Sinaga Nation, Malaysia, for bringing in the international perspective to the FDP. Dr. Mangala Rajalu Ramalinga Vishwanathan, Professor, University of Atrobat, Chile, for gracing this program with his vast global experience in material science and engineering. Your extreme presence and valuable knowledge sharing will, no doubt, enrich the academic and research outlook of our participants. Once again, I extend my heartfelt congratulations to the Department of Physics for organizing this meaningful academic innovatives and wish the FDP a grand success. Thank you all.
Thank you, ma'am. Now I invite Dr. E. Annie Ratnakumari, Assistant Professor at Department, to introduce our speaker of the day, Dr. Muthu Sendil Pandian. Ma'am, over to you.
A very good morning to everyone. It gives me immense pleasure to introduce our distinguished resource person for today's faculty development program, Dr. Muthu Sendil Pandian. Dr. Muthu Sendil Pandian is currently serving as research scientist, senior PhD, and research coordinator at SSN Research Center, SSN Institutions, Chennai. He also holds prominent academic leadership roles as the Vice President of Indian Association for Crystal Growth and Executive Member of the International Organization for Crystal Growth. He is the Fellow of the Academy of Sciences, Chennai, a recognition of his outstanding contributions to science. His research interests cover a wide spectrum of advanced materials, including bulk crystal growth by solution and melt techniques, non-linear optical crystals for ferroelectric and thermoelectric applications, and also on perovskite and dye-sensitized solar cells, quantum dot solar cells, nanomaterials, and thin films. His research contributions are truly remarkable. He has successfully completed 31 funded projects from prestigious agencies including PRNS, SERV, DST, UGC, CSIR, and international collaborations with a total funding of rupees 390.52 lakhs. He has authored 236 international journal publications, 35 international conference proceedings, and presented over 430 conference papers. He has also contributed 42 books, book chapters, and proceedings, filed 8 patents, and deposited 32 new crystal structures in the CCDC database. His impactful work is reflected in 4,373 citations, an H index of 33, and an item index of 120. In recognition of his excellence, Dr. Muthu Sendil Pandian has received 38 international and national awards, delivered 186 invited and special lectures, and have organized international and national conferences, such as career in crystal growth, solar cell research, and advanced materials. Dr. Sendil Pandian continues to inspire researchers and academicians worldwide. We are truly honored to have him with us today. On behalf of the organizers and participants, I extend a very warm welcome to Dr. Muthu Sendil Pandian, and we look forward to an enlightening and thoughtful provoking session. Now I hand over the session to you, sir.
Thank you, Dr. Rani, for your wonderful introduction, and very good morning. I'm very delighted to be here on this wonderful occasion of delivering my lecture in this FDP. First of all, I'd like to thank the organizers, the HOD, Dr. Sivagami, and the FDP coordinator and my very good friend, Dr. Ani Ratnakumari, and the FDP co-coordinator, Dr. Piyula, and all the organizing committee members of this department for giving me this wonderful opportunity to share some of my recent research work in bulk crystals. Just sharing my PPT, please check. And this is the title of my today's lecture, and physics of single crystals for technological applications. And I myself, Muthu Sendil Pandian, working as a faculty in SSN Institution, Chennai. Growth of high quality and large size and unidirectional with higher physical properties. With higher physical properties means with higher mechanical hardness, optical transmittance, higher optical homogeneity, with good crystalline perfection is still very challenging task for crystal growers by solution growth method. High quality single crystals is of great importance when it comes to the device making. In this lecture, I am going to present you a method which gives you the crystals of very high quality. All the crystals, whatever you are going to see in my slides, are grown by three different techniques, namely SCST, SR, and RSR. SCST means slow evaporation solution growth technique in a very small size beaker. We have grown a lot of technologically important NLO and ferroelectric single crystals, but we cannot use it directly for the practical device application. In order to use it for the societal benefit for practical device application, we identify the highly efficient and stable single crystals, and we grow the crystals by the SR method, Sankaranarayan and Ramasamy method, invented by two professors from the Alagappa University, Karaikudi in the year of 2005. So this is the outline of my today's lecture and introduction. What are the importance of single crystals? Crystal growth by conventional method at room temperature. We have grown a lot of technologically important single crystals. And what are the drawbacks when you grow the crystals by this conventional method? And we also grow the crystals by this unidirectional SR method. And what are the advantages when you grow the crystals by this unidirectional method? Under identical condition, we compare the physical properties and the crystalline perfection of the two method grown crystal, SCST and SR. And in order to identify the growth phenomena, we have selected the shadowgraphy and the maxillary interferometric technique with the help of RRK Tindur, Department of Atomic Energy in Indore. And this is a special material, TGS, triglycerin sulfate. The specialty of this material is, so at its, the Curie point of this TGS is 49 degrees Celsius. Below this Curie point, the material belongs to the ferroelectric nature. Above this Curie point, the same material belongs to the paraelectric nature. One is monoclinic crystal system, another one is the orthorhombic crystal system. And we have identified the Curie point, and we successfully grown the crystal at its ferroelectric nature and crystal at its paraelectric base. Under identical condition, we compare the ferro and the para, which is more suitable for the higher data application. And in order to overcome all these issues like multinucleation, microcrash present in the conventional SR method, we have done several modifications in the conventional SR method. It is called as a RSR and ISR technique, rotational Sankaranarayan Ramasamy method, and immersible ample SR method. And with the help of Dr. Sunil Verma from RRK Tindur, we have successfully fabricated the 4-nitrophenol type 1 type 2 SGH element, and finally we compared the physical properties and crystalline perfection of the all the three method grown the crystals. And finally I conclude my lecture. So single crystals forms an indispensable part of the rapidly advancing technology. The art of growing these kind of single crystals has turned into science with a variety of wide range of application. And a variety of single crystals find applications in lasers, nonlinear optics, LED, piezoelectric detectors, optical components, and so on. So the availability of these kind of single crystals is equal to the ability to rise the country's economy. The ability to grow these kind of single crystals is an essential criteria for the competitiveness of our nation. All the crystals are grown in our laboratory, grown by this SR method. These are some of the very good ferroelectric and NLO single crystals for practical device application. And crystals can be grown from three different techniques. One is solution, melt, and vapor technique, in which solution and melt techniques are most commonly useful for the practical device application. And these are some of the invention of crystal growth methods available to grow the technologically important single crystals. You see, from 18th century, 1851 hydrothermal method, Verneuil, Zagorski, Bridgman, there are a lot of solution and melt techniques are available to grow the technologically important single crystals. In the year 2005, Professor K. Sankaranarayan, now he is head of the Department of Alagappa University, Karigudi, Department of Physics, and Professor P. Ramasamy, he was the former vice chancellor of Alagappa University. Both they invented this method, unidirectional solution crystallization method. It is also called as a Sankaranarayan and Ramasamy method. So far, by this method, more than 500 numbers of crystals are successfully grown. So we can able to grow the organic, inorganic, semi-organic, positive soluble, negative soluble, all kind of crystal can be possible by this method. These are some of the classification of nonlinear optical single crystals. It can be classified as organic, inorganic, and semi-organic single crystal. The main advantages of this organic single crystal is we can get the very high efficient comparable to the standard KDP potassium dihydrogen phosphate. Still, they are using for the laser application. The SKG efficiency of this organic crystal is very high, and but the problem is we cannot grow the crystals as a bulk form. But in the case of inorganic single crystals, we can be able to achieve the bulk size. But if, like organic, we cannot achieve the high efficiency in the inorganic material. So the crystal growth researchers, what they are doing now is they select the one organic material, one inorganic material. They combine, they will get the hybrid material. It is also called as a semi-organic single crystal. So like example, glazine is an organic material, barium chloride is an inorganic material. They synthesize the glazine and barium chloride like 1:1, 2:1 molar ratio. They prepare the solution, they filter, and they pour the solution in the beaker. They will get the semi-organic single crystals. The main advantages of this semi-organic single crystal is we can easily achieve the efficiency and we can also easily grow in the bulk form. This is the main advantages of the semi-organic single crystals. These are some of the properties that needed for the nonlinear optical single crystals. Before we go for the actual crystal growth, crystal characterization, crystal device making for practical utility, we have to ensure all the properties like it should be high nonlinear optical coefficient. For laser application, one must ensure the laser diameter threshold value of the grown crystal. So we have to carry out the single and multi-share laser diameter threshold, fast optical response time, wide transparency range in the range of UV, visible, and IR region. So 200 to 1100 nanometer, the optical transmittance of your crystal should be very high for any kind of optical application and should be high thermal stability and mechanical stability, high chemical stability, ability to process into the crystal, and also the device fabrication should be very easy. These are some of the conventional method grown 2-amino 5-nitroprotein derivative single crystals for nonlinear optical application. All these crystals we have grown in a beaker, small size beaker. So when the solvent evaporates, the remaining solidity particles approaching the surface directly. So the surface attracts more atoms very easily. The small embryo nucleation will be formed, and then the crystal will be grown like this. When we grow the crystal at room temperature, you see because of the temperature fluctuation of the daily variation, the issues like solvent inclusions, microcracks, milky opaques will be appeared. Almost all the conventional method grown crystal, and this project is supported by SERB. Now it is called as ANR of Government of India. The ultimate aim of this project is to grow this kind of 2A, 5NP, 2-amino 5-nitroprotein derivative single crystal along its unidirectional bulk size single crystals with higher physical properties and crystalline perfection for nonlinear optical application. In order to overcome these issues like solvent inclusions, microcracks, milky opaques, what we have done is we select the same this highly efficient crystal. We identify the morphology using single crystal X-ray diffraction measurement. We identify their direction and we mount at the bottom of the glass sample. We pour the solution. We apply the temperature at top portion of the glass sample. The solvent is evaporated. The crystal will be grown like this. So these are the crystals grown by conventional method with higher efficiency, but we have to improve the physical properties, crystalline perfection, and we have to grow the crystal with the bulk size along its unidirectional. So the same seed crystal we select and we grow this much of large size single crystal for optical application. These are the as grown the same 2A 5NP crystals, and these are the cut and polished wafers. And several attempts have been made to grow the crystals by slow evaporation method, slow cooling, seed rotation, and melt growth method like Bridgman, Zagralski, float zone melting, and flux growth method. But all the reported methods at elevated temperature that leads to thermal induced growth defects and very complicated equipment, difficulty in growing large size single crystal. There are a lot of multi-step processes are also involved. These are some of the crystals grown by conventional method. When we grow the crystals in a beaker, petri or crystallizer, the crystal will be grown like this. And we have to identify the morphology using single crystal X-ray diffraction method measurement. Whether we wish to grow the crystal along its A direction, B direction, C direction, or if it's a non-distributed crystals, we have to identify the phase matching direction, and we have to grow the crystals by this SR method. These are the one more 4 interval derivative single crystals for nonlinear optical application. When we grow the crystal, we immediately identify the direction using single crystal X-ray diffraction, and we grow the crystal by this SR method. These are some of the conventional method grown 4 interval derivative single crystals supported by DAE BRNS, Department of Atomic Energy. So here also we identify the highly efficient material and we grow the crystal by SR method for nonlinear optical application. And these are the conventional method grown tricycle derivative single crystal by SEST method, slow evaporation solution growth method. All the crystals are grown by SEST method. In a beaker, we have grown these crystals for nonlinear optical application. And these are some of the conventional method grown nonlinear optical and ferroelectric application. And what are the disadvantages when we grow the crystals by this SEST method? Due to temperature fluctuation of the daily variation, multinucleations will be formed. There are a lot of microcracks will be appeared in the during the growth. There are also milky opaques formed in the conventional method grown crystal, and we cannot grow the single and the bulk size single crystals when we select the SEST method. And these are some of the Grosseter boundaries appeared in the conventional method, which we cannot avoid in the all the SEST method. Because of this lot of Grosseter boundaries, the dysluxation density of this SEST method grown crystal is very high. This we can easily identify using chemical etching measurement, and we cannot grow the crystal with high uniformity. And the entrapment of solvent molecules into the crystalline matrix is only responsible for appearing these kind of low angle grain boundaries in the conventional method grown crystal. Not only this TGS and sulfamic acid, almost all the conventional method grown crystals are having these kind of issues like multinucleation, microcracks, milky opaques, high dislocation density, no uniformity, solvent inclusions, and so on. These are conventional method grown 4 nitrophenol derivative single crystal, AAP4N single crystal. If you identify any one single crystals, all the single crystals are having different planes, bases, Grosseter and Grosseter boundaries. But for application point of view, device point of view, phase matchable portion is only useful and other portion will be cut after cutting the phase matching angle. For devices like frequency doublers and optical parametric amplifiers, phase matching needs to be achieved. Otherwise, the convention efficiency would be very low. In this point of view, this SR method has given the solution and it is possible to grow the crystal along its phase matching direction. Along whatever direction you want, you can grow by this method. Whether we wish to grow the crystal along its different direction, before we mount the crystal, we have to identify the direction of your grown crystal. So this is the diglycine barium chloride. This is the SSD gas, sodium sulfonylate dihydrate single crystals for nonlinear optical application. And this is the SKG element making of KDP, potassium dihydrogen phosphate single crystal. The morphology of the KDP shows the phase matching direction of the KDP is 59 degree. So what we have to do is we have to cut the using single crystal X-ray diffraction measurement. We have to identify the phase matching direction and we have to cut the crystal along its phase matching direction using fine AXA blade and frame, and we have to mount at the bottom of the glass sample. Then we have to pour the solution. When we apply the temperature, the crystal will be grown along its phase matching direction. So this is the phase matching direction of this KDP single crystal grown in RRK Tindur. The same KDP crystal grown in our laboratory SSM. And this is all the crystals are same. This is the conventional method grown 2-amino 4-nitrophenolate 4-nitrophenol single crystals for nonlinear optical application. This 2AP4N single crystals grown by SCSG method, and this is the crystal grown by SR method. This is the crystal grown by the RSR method, and the same crystal we have also grown by the point seed rotation technique. From these point seed rotation techniques, we have successfully fabricated the type 1, type 2 SKG element for optical application. For this SR method, as I mentioned, but here what we have done is we mount the seed crystal with the C direction, dominant plane, and we grow this much of large size single crystal. But in the case of conventional SR method, there is no way to go out the impedance in the SR method grown crystal, but we have to reduce the impedance segregation in this SR method in order to get the crystals with higher physical properties and good crystalline perfection. So we have made a slight modification in the SR method, conventional SR method. It is called as a RSR method. Here, what we have done is we have made several slats and holes in the SR glass sample. We completely rotate the experimental setup of this RSR method with the seed crystal, with the solution, with crystal. The complete experimental setup should be rotated so that the impurities are pushed out from the glass sample. One can easily minimize the impurity segregation in the RSR method grown crystal. Once we can able to minimize the impurity segregation, then automatically the physical properties like optical transmittance, mechanical stability, dielectric permittivity, optical homogeneity of your RSR method grown crystal will be enhanced. So just for your example, this is a TGS crystal grown by conventional method. As I mentioned, the only polar B direction will be useful and the other portion will be cutted after cutting the polar direction will be wasted. More than 99.9% will be wasted after cutting this polar B direction. So we identify the polar direction and we mount, we grow this much of large size single crystal. This is one more example, glycine phosphate. We grow the crystal along its polar B direction. So the crystal growth techniques for the present investigation mainly concentrated on this Sankaranaya Ramasamy method and SCSG method. For the growth of the crystal by this SR method, the large size single crystal, we have to ensure and we have to optimize, we have to select all these parameters very carefully. That is instrumentation, synthesis and conventional crystal growth, selection of different seed crystal direction, and depends upon the solubility of your material, whether your material is having the low soluble, moderate soluble, and high soluble. Then you have to select the different sizes of the glass sample, ID and OD, inner diameter and outer diameter, and the unidirectional crystal growth. Growth optimization means you have to maintain the two different temperatures in the SR method. One is for solvent evaporation rate, other temperature at bottom side near the crystal solution interface. You have to maintain the uniform temperature, otherwise there is a large possibility in the formation of microcracks, solvent inclusion, milky opaques in the SR method glass sample. So two different temperature. If it is a very known material, then you can easily identify the temperature, optimize the temperature using the literature survey. You can fix the temperature. If it is a new material, you have to optimize yourself with different temperature at top and bottom portion. Normally, for semi-organic or organic or inorganic crystal, any kind of crystal, we usually maintain the temperature between the 36 to 40 degrees Celsius. So at 30 degrees Celsius, 36 degrees Celsius, what is the growth rate? 37, 38, 38, 40. Then you have to optimize yourself for the new material. And finally, growth rate measurement. This growth rate is mainly depends upon the temperature what you have applied at the top temperature, top portion, and the size of the glass sample and the direction you have selected for the bulk growth. The experimental setup of this SR method consists of the glass sample. This glass sample is kept inside this water bath and a thin plate like seed crystal is mounted at the bottom of the glass sample, and then you have to pour the saturated solution inside the glass sample. After few hours, due to gravity-driven concentration, all the solid molecules are approaching the crystal surface directly. The seed crystal attracts more atoms very easily. So there is a high concentration at bottom portion, low concentration at top portion. So immediately the plumes are started from the bottom of the glass sample. The plume is nothing but the movement of fluid flow from the high concentration to low concentration. Usually the plumes are started at the bottom of the glass sample. It is moving upwards between the high concentration to low concentration. Then new plumes are started from the bottom of the glass sample. So the process will be happening continuously. So the crystal will be grown like this along its particular direction, in direction. Then you have to apply the two different temperature at top and bottom portion. The top of this temperature is only for solvent evaporation. The bottom of this temperature is for growing the crystal. This solution and crystal interface, you have to maintain the uniform temperature. If there is a small fluctuation, then immediately multinucleation will be formed. So automatically the microcracks, milky flakes will be formed in the SR glass sample. So it should be very carefully maintain the uniform temperature between the crystal and solution interface. To avoid the temperature fluctuation of the daily variation, water is frequently added inside this water bath. You have to maintain the uniform water level. Otherwise, you cannot maintain the uniform temperature at top portion. To avoid the fungus formation, a freshly prepared saturated solution is frequently added inside the SR glass sample. Then you have to maintain the uniform solution level also. So after a few weeks or few months time, depends upon the solubility of your material, the direction of your growth, the crystal will be grown like this. So this is the diglazine barium chloride single crystals for nonlinear optical application. So this is the complete experiment setup of this SR method. So this is the crystal counting and mounting process using fine AXA blade and frame, and you have to cut the crystal along whichever direction you want. So this is the TGS crystal, as I mentioned. Only this small portion, polar B direction, will be useful for the iodinator application. So using fine AXA blade and frame, you have to cut like this, and you have to make it as a thin plate like a seed crystal, and you have to mount at the bottom of the glass sample. Then you have to pour the saturated solution. So it will be like that. So this is a schematic diagram of this crystal cutting and mounting process. This is the actual original TGS crystal is growing in a glass sample along its polar B direction. So we mounted the seed crystal here at the bottom of the glass sample. So this much of large size transparent crystal can be grown by this method for iodinator application. This is the glass sample, and we pour the saturated solution inside the glass sample. This is outside the water bath. See, what are the advantages of this SR method? So single crystal with a specific orientation and glass sample. So this is the TGS crystal. This is the crystal, the same TGS crystal grown along its C direction, B direction, A direction. So whatever direction you want, you can grow by this method. Easily we can find out the growth rate along any different plane. This is the lysine monohydrochloride single crystal for nonlinear optical application. So this much of large size crystal can be possible by this method. If you wish to identify the growth rate along any different direction, because we know the crystal is anisotropic nature, so we wish to identify the growth rate along any different direction, you have to cut the crystal at a different direction, and you have to select the glass sample, and you have to select the saturated solution, you have to select the seed crystal thickness. Everything should be identical. You have to mount and you have to pour the solution. You have to apply the identical temperature for the different direction, and you can easily measure the growth rate along any different direction. So the entire quantity of the solution is converted into the crystal. So if you pour the 5-liter solution, if 2.5 kilogram of TGS crystal was saturated in that solution, then you will get the 2.5 kilogram of the TGS crystal along its unidirectional. So this is the 25 centimeter longest TGS crystal grown by this SR method. We mount the seed crystal at the bottom of the glass sample. So this much of transparent crystal can be possible by this method. It is started and it is end up at the top of the glass sample. So with a thin plate like a seed crystal, this much of large size crystal can be possible by this method. So you see from this 2 mm thickness, one can easily achieve this much of large size. This is the SSD gas, sodium sulfur diode single crystals. You see 9 centimeter length, 2.5 centimeter diameter crystal was possible by this method. And he is one of the inventor of this SR method, Professor P. Ramasamy, former Vice Chancellor of Alagappa University. And he is holding the organic benzamidine single crystals for nonlinear optical application. And the scaling up was relatively very simple by this method when we compare the melt growth technique like Zagorski-Bridgman. So this method was very simple. So normally in conventional method, the crystal will be grown like this. A small embryo will be formed when the saturated solution will be evaporated. Then the nucleation will be formed from the small size nanometer, then micrometer, then millimeter, then centimeter. The crystal will be grown like this. Suppose this is the direction you want for any optical application. This is the phase magic direction. You see, this is the 1-day growth, this is the 2-day growth, and this is the 3-day growth, this is the 4-day, 5, 6, 7, 8, 9, 10. So there will be no uniformity in the conventional method grown crystal. But in the case of SR method, it is a layer by layer growth. It is a layer by layer growth comparable to the conventional method. The optical homogeneity of this SR method grown crystal is very high. This we have identified using the Bayer-Vincenz measurement. So the requirement of large size crystal growth chamber is avoided in this SR method. If you wish to construct this SR method in your UG, PG or PhD research laboratory, so within 5,000 rupees, one can easily construct this SR method in your laboratory. To construct this SR method, you need only this 1 feet crust, 1 feet water bath. This water bath is nothing but the usual fish tank only, and two RTD temperature controller with sensor to sense the temperature at top and bottom portion, two ammeter and two transformer, and very simple wire connections are there. So within 5,000 rupees, one can easily construct this method. So this is the crystal grown by conventional method. We have grown the crystal along its C direction, dominant plane. So we mount the seed crystal at the bottom of the glass sample. We pour the solution. We apply the temperature. So the crystal is growing from the bottom to top. So this is the crystal grown by conventional method. This is the crystal grown by the SR method. These are the cut and polished wafers from this SR method grown crystal. So not only cylindrical shape depends upon the shape of the crucible. Any shape can be possible by this SR method. If you wish to grow the crystal in a prism in shape, square in shape, rectangle in shape, all shape can be possible. You have to identify the shape and you have to mount the crystal. So for any shape can be possible by this method. So normally in conventional method, the KDP crystal will be grown like this, but depends upon the pH of the solution, one can easily enhance or suppress the growth rate along any different direction. That you have to optimize yourself with the different temperature, with the low and high pH of the solution, and we grow the crystal by this SR method. So the crystals which have pro-slope cracking tendency can be grown without resulting in the post-slope cracking tendency. So this is the crystal grown by the conventional method because of the temperature fluctuation of the daily variation. There are a lot of microcracks will be formed in the conventional method grown crystal, but in the case of SR method, we have maintained the uniform temperature at top and bottom portion. So there is a stable supersaturation and uniform solvent evaporation rate, uniform growth rate. There is no chance in the formation of microcracks, milky opaques in the SR method grown crystal. So the crystal quality is always superior to the conventional method grown crystal. This we have identified with several characterization. Under identical condition, we measure the physical properties and crystalline perfection of the two method grown crystal, SCST and SR method grown crystal. And this is the HRXID, Bayer-Vincenz, and chemical etching, optical transmittance, Vickers microfurnace. We have carried out a lot of characterization to identify the physical properties and crystalline perfection of the SCST and SR method grown crystal. As I mentioned, so far we have grown more than 500 numbers of crystals, and we can able to grow the low soluble material, moderate, high, positive, and negative soluble material. All kind of material can be possible by this method. And this is the low soluble KAP, and this is the moderate soluble TGS, and this is the very high soluble benzophenone, 265 gram per 100 ml. This is a very big, very high soluble material, and this is the negative soluble lithium sulfide monohydrate single crystal for NLO application. And based on our experience in the unidirectional growth, we have attempted to grow the world's longest crystal. The total length of the ground crystal was more than 1 meter, 135 centimeter length, and with 5.5 centimeter diameter. With the help of Dr. G. Bhagavan Narayana, we have successfully achieved this. And in fact, we have tried this in 2007, and we have successfully grown this much of large size crystal in 2011, and we have reported in 2012. So this is the experimental setup of that 8 feet setup, and we have maintained the one temperature at bottom portion and one temperature at top portion. And the top portion, we applied the temperature like 39 and 40 degrees Celsius for solvent evaporation rate, solvent evaporation. And we have selected the xylene. It is a very good solvent for the benzophenone material, and the crystal is growing from the bottom to top. So this much of large size transparent crystal can be possible by this method. And this is the morphology of this KDP, benzophenone single crystal. You see the 100 direction we have selected because the growth rate along this direction is very high comparable to all the other direction. This is the different growth stages of this organic benzophenone single crystal for nonlinear optical application. So this is the 85 centimeter length, and this is the 1350 mm length of the benzophenone single crystals for NLO application. This is the organic material. Similarly, we have grown a lot of technologically important single crystals in the glass sample. Then how to harvest the crystal from the glass sample? You see, this is the 25 centimeter longest TGS crystal. As I mentioned, you have to maintain the two different temperature. One is at top portion and another one is at the bottom portion. And top, you usually may maintain the high temperature like 38, 39, 40, 41 degrees Celsius. And you have to reduce the temperature like 1 degree Celsius per day or 0.5 degrees Celsius per day or 0.1 degree Celsius per hour. So it depends upon the solidity of your material. You have to reduce the temperature like that, and you have to wait until it reaches the room temperature. Once it reaches the room temperature, and you have to kept out from the water bath. So this is the crystal inside the water bath. This is the crystal outside the water bath. Then using this diamond coated wheel cutter, you have to remove the top and bottom portion separately. And this is the 25 centimeter longest TGS crystal inside the glass sample. And then using the diamond tipped glass cutter, we all know the glass cutter, you have to mark the top and bottom portion separately and very slowly. And using the soft knife things, you have to remove the glass sample very slowly. So this is the TGS crystal along its polar B direction without any glass sample. Then how to cut the crystal? So this is the diamond coated wheat cutter crystal cutting machine supported by DIBRNS, Department of Atomic Energy. So this is a speed controller. Before we mount your crystal, you have to measure the mechanical stability of your ground crystal using Vickers micro hardness. So whether your crystal belongs to the mechanically soft or very hard, using Vickers micro hardness. And the ethylene glycol is kept inside this tray. The ethylene glycol is act as a coolant material. So we have to cut like this, and this is almost cut portion of this TGS crystal, almost cut portion. So this is the cut portion. This is the actual TGS crystal grown by SR method. So this is the 25 centimeter longest TGS crystal at its bottom, middle, and top portion. Now we are going to see some of our laboratory grown NLO single crystal, SSGH, cotton polished wafers, diglazing zinc chloride monohydrate single crystals for NLO application, cotton polished wafers, and this is the 2-amino 5-nitroprotein derivative single crystals for NLO application, as grown and cotton polished wafers, and this is the ferroelectric glazing phosphate single crystals for iodator application. These are the cotton polished wafers of glazing phosphate, and this is the 4-nitroprotein derivative single crystals for nonlinear optical application, and this is the low soluble KAP, and this is the triglazine sulfate single crystal for ferroelectric application, and this is a sodium para-nitroprotein single crystals, and we have selected the dominant 001 C direction for NLO application. So this is the crystal inside the glass sample, and this is the crystal without glass sample. These are the cotton polished wafers, and this is the diglazine barium chloride monohydrate single crystals for nonlinear optical application, as grown cotton polished wafers, and this is the lab single crystals for NLO application, and this is the ammonium tartrate single crystals for nonlinear optical application. So before we proceed for the actual conventional growth and characterization and unidirectional growth and characterization to identify the physical properties and crystalline perfection, you have to identify the material. You have to do the material confirmation using the single crystal X-ray diffraction measurement to check the crystalline perfection of your ground crystal. And we are used the HRXD, high resolution X-ray diffraction measurement. Using the FWHM full width at half maximum, one can easily identify the crystalline perfection of your SCST and SR method ground crystal. To identify the dislocation density of your ground crystal, we have selected the chemical etching measurement. And to identify the crystal for the laser applications, we have carried out the laser diameter threshold value. To identify the mechanical stability, Vickers micro hardness. To identify the optical quality, UV and IR. And the electrical measurement, we have carried out the dielectric permittivity and dielectric loss. To identify the optical homogeneity, we have carried out the Bayer-Vincenz measurement. So samples were prepared with identical thickness. Samples means crystal grown by this SEST, small size and large size SR method. The surface damage is affected by the energy absorbing defects such as stains, scratches, and the polishing contaminant, which strongly influence the physical properties. Therefore, all the characterizations were performed on the highly polished crystals so that one can easily minimize the any surface defects like solvent inclusions, microcracks, mildew, opaques in the SEST and SR method grown crystal. And in order to confirm the reproducibility, almost all the characterizations were repeated on the several times, and almost similar results have been observed for the SEST and SR method grown crystal. So this is the HRXD measurement for the sulfamic acid. And because of this lot of microcracks, milky opaques, and the entrapment of solvent molecules into the crystalline matrix is only responsible for appearing this kind of more satellite peaks in the SEST method ground crystal. But in the case of SR method, no microcracks, milky opaque, solvent inclusion. The FWHM full width half maximum of this SR method ground crystal is very low, 5.5 hours again, which clearly indicates that the crystalline perfection of the SR method grown crystal is very high, superior comparable to the conventional method grown crystal. And this is the one more confirmation, SSD single crystal, that pink color crystal. And because of the solvent molecules, solvent inclusions, lot of satellite peaks are appeared in the SEST method grown crystal. But in the case of SR method, and single and very sharp peak and low FWHM, which clearly indicates that the crystalline perfection of the SR method grown crystal is very superior. And chemical etching is an important or powerful tool to identify the dislocation density of your ground crystal. And you see the number of dislocations, number of HPs appear in the SCST method ground crystal is very high comparable to the conventional method ground crystal. From this picture, one can easily identify the dislocation density of your ground crystal, and number of HPs divided by area. You can easily calculate the dislocation density value. So number of HPs you have to count the manually, and divided by area, length into breadth, you will get the area. So number of HP divided by area, you will get this value. You see, low dislocation density, which clearly indicates that the crystalline perfection of this SR method ground crystal is very high. So this is for 5 seconds and 10 seconds for the SCST. This is similar way we have carried out for the SR method ground crystal also 5 seconds and 10 seconds. And successive etching from the 5 to 10 seconds, the HPs enlarge the size, retaining the geometrical shape and do not disappear, suggesting that the bits are due to dislocation. The dislocation density of this SR method ground crystal is 3.5 into 10 power 2 centimeter power minus 2. But in the case of SCST, it is very high. You see, the number of HPs is very high in the SCST method ground crystal comparable to the SR method ground crystal, and randomly distributed but strictly oriented HPs have been appeared for the SCST and SR method ground crystal. These are the various type of defects observed in the SCST method ground crystal. Not only this TGS, almost all the conventional method ground crystals are having this kind of issues like inclusions, low angle grain boundaries, microcracks, milky opaques, microcrystallites, and so on. But in the case of SR method, it is a single and a morphological defined facet. There will be no Grosseteste boundaries, which clearly indicates that the crystalline perfection of this SR method ground crystal is superior comparable to the conventional method ground crystal. It has been already observed that the dislocations have been originated from the Grosseteste boundaries. But in the case of conventional method, you have to grow the crystal with well-defined morphology. There is no option. But in the case of SR method, it is a single and morphological defined facet. To check the mechanical stability of your ground crystal by SCST and SR method, we have carried out the Vickers micro hardness. This blue color indicates for the SR method ground crystal, and the red color indicates for the conventional method ground crystal. And because of the higher crystalline perfection, the mechanical stability of this SR method ground crystal is high. But in the case of conventional method ground crystal, low FWHM and high number of dislocation densities, solvent inclusions, microcracks, milky opaques, the mechanical stability of this conventional ground crystal is less comparable to the SR method ground crystal. And this is one more confirmation for the glassine phosphate, higher mechanical stability for the SR method ground crystal comparable to the conventional method ground crystal. For conventional, it is 56 kg per millimeter square, but in the case of SR method, it is 81 kg per millimeter square. And because of the higher mechanical stability, the number of microcracks appeared near the indentation is very high. But in the case of conventional ground crystal, it is very less. This is the 25 centimeter longest TGS crystals. We have checked the uniformity of this bottom, middle, and top portion. We see the mechanical stability of this crystal grown by the SR method at its bottom, middle, and top is almost same. The main reason for the observing lower mechanical stability of this conventional ground crystal is only solvent inclusion. So the variety of parameters such as variation in supersaturation during growth, minor fluctuation in temperature, and non-uniform growth rates are governed the solvent inclusion. These are the solvent inclusion patterns appear for the NaCl and sodium chloride single crystal. These are some of the solvent inclusions appeared, and we have captured this in our optical microscope. But in the case of SR method, as I mentioned, we have maintained the two different temperatures. So uniform temperature, stable supersaturation, stable solvent evaporation rate, uniform growth rate. There is no chance in the formation of solvent inclusion in the SR method ground crystal. And we have also carried out the Lacedemeth threshold value for the SCST and SR method ground crystal. Because of the higher mechanical stability, no solvent inclusion, the Lacedemeth threshold value of the SR method ground crystal is high, 17 millijoule per centimeter squared. But in the case of conventional method ground crystal, and because of the low mechanically stable and high number of dislocation density, it was only 12 millijoule per centimeter squared. This is one more confirmation for the benzophenone single crystal, 15 millijoule per centimeter square for the small size single crystal by SCST method, and 19 millijoule per centimeter square for the large size single crystal grown by the SR method. And the dielectric permittivity of your crystalline material is a second rank tensor. For orthorhombic crystal, there are 3 independent components. For monoclinic crystal, there are 4 independent components. This is the gold coated sample we have used for the dielectric permittivity and dielectric loss measurement. For these orthorhombic crystals, we have identified the direction of the A, B, and C direction, the SR method grown SSD single crystal, and we have carried out the dielectric permittivity and dielectric loss value for this crystal. Anisotropic in the dielectric behavior was observed with the SR method ground crystal, and this blue color indicates for the A axis, red color for the B axis, green color for the C axis. Anisotropic in the dielectric behavior, and higher value of dielectric permittivity and lower dielectric loss, which clearly indicates that the optical quality of this SR method ground crystal is very high. And this is the one more confirmation. This is that special material TGS, triglycerin sulfate single crystals for ferroelectric application. The Curie point of this TGS is 49.5 degrees Celsius. Below this Curie point, the material belongs to the ferroelectric nature. Above this Curie point, the material belongs to the ferroelectric nature. Using this modified SR method, we have successfully carried out the growth at its ferro and ferroelectric, and we have compared the physical properties and crystalline perfection. And to identify the optical quality of the SCST and SR method ground crystals, you have carried out the UV NER. You see both are looking very transparent, but in the case of microscopic images, you see this is for the conventional method ground crystal, this crystal, and this is for the SR method ground crystal, this large size single crystal. Both are looking very transparent, but in the case of conventional method ground crystal, lot of solvent inclusions, microcracks, milky opaques, so the surface is very rough. But in the case of SR method ground crystal, no solvent inclusions, microcracks, milky opaques, and less dislocation density. So the surface is very smooth. So if the surface is very smooth, so the optical scattering centers of this SR method ground crystal is very low, so that the no scattering and the output intensity will be very high. So the optical transmittance will be very high in the SR method ground crystal. But in the case of conventional method ground crystal, lot of scattering centers will be there in the conventional ground crystal that causes the lot of scattering. So the output intensity is very less, that causes the low optical transmittance. So high optical transmittance in the SR method ground crystal and a low optical transmittance in the conventional method ground crystal. This is one more confirmation for the diglazine zinc chloride aggregated single crystal. 11% is high optical transmittance in the SR method ground crystal comparable to the conventional method ground diglazine zinc chloride single crystal. And to check the optical homogeneity, we have carried out the single crystal birefringence measurement. The optical homogeneity of this SR method ground crystal is very high. So just a simple comparison between the conventional, this SR method ground crystal. In the case of conventional method ground crystal, you see there are a lot of Grosvenor boundaries, solvent inclusions, scattering centers, microcracks, milky opaques, dislocation density. So the physical properties is low and the crystalline perfection also very low. But in the case of this large size crystal grown by the SR method, no Grosvenor boundaries, no solvent inclusion, less scattering centers, no microcracks, milky opaques, and less dislocation density. The physical properties such as optical transmittance, mechanical stability, of the SR method grown crystal is very high. The crystalline perfection also we have checked with the HRXID and chemical etching measurement. The crystalline perfection of this SR method grown crystal is very good and superior comparable to the conventional method grown crystal. And to identify the the growth phenomena of these SR method grown crystals, we have carried out the shadowgraphy and the Max-Zeta interferometry with the help of RRK Tindu. And this is the actual seed crystal along its BA direction for the benzobenone we have selected, because the solubility of this benzobenone is very high. So within 1 week time, we can easily complete the growth phenomena characterization. And we have performed the real-time in situ optical imaging of concentration and convection field during the SR method growth of the benzobenone crystal. The shadowgraphic technique is used to visualize the convection to quantify the thickness of the solidal boundary layer and the crystal growth rate for the high soluble benzobenone crystal. And the Max-Zeta interferometry used to quantify the gravity-driven concentration profile during the growth for the SR method. Almost 1 week time, we have carried out these two measurements. This is the borosilicate glass crystallizers we have selected for the imaging technique. This is the laser setup we have used in RRK Tindur. We mounted the seed crystal here. We pour the solution and we slowly cool the temperature from high temperature to lower temperature from room temperature. This is the 3 different growth stages of this imaging technique. So we mount the seed crystal, we pour the solution. The surface roughness was happening in the benzobenone crystal. This is the actual point what we want to measure, the shadowgraphy and the Max-Zeta interferometry between the crystal and then solution interface. You see, this is the complete profile using the shadowgraphic images. So first one day, you see the concentration at bottom portion is very high comparable to the top portion. This is the next 5 day, and this is the 11th day. After 11th day, the plumes are started from the bottom of the glass ampoule. The plumes is moving the fluid flow from the concentration, high concentration to low concentration. The plume is started growing from the bottom to top. Then the crystal is growing very transparently. So if you concentrate any one plumes, all the plumes are formed at the bottom of the SR growth method, and the plume is moving upwards, 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 and finally it's disappeared, and then new plumes are started from the bottom of the glass ampoule. From this shadowgraphy and Max-Zeta interferometry, one can easily conclude that the gravity-driven concentration is only responsible for the growth of the crystal by this SR method. Excuse me. This is that special material I mentioned in my second slide, the TGS crystal, triglycerin sulfate. So we grow the crystal at its ferro and parallel capacitor, and we measure the solubility of the ferro and parallel nature. So this is the experimental setup we selected in the RRK Tindur for the below TC 36 degrees Celsius for solid operation rate. So
Hello, sir.
yes, madam.
So sorry to interrupt. As you have requested, you can extend the presentation for 5 more minutes. After that,
Yes.
we can have question and answer
Within
sessions.
5 minutes, I
Okay,
will
sir?
complete. Yes.
Okay, sir. Thank you. Thank you, sir.
For below TC, we have maintained this temperature and we grow the crystal. For above TC, we maintain the temperature, identical temperature at top and bottom portion, 54 degrees Celsius, and we grow the crystal under identical condition, identical thickness. So we measure the D3 coefficient, piezoelectric D3 coefficient. You see the D3 coefficient of the parallel capacitor grown crystal, 35 picocoulomb per Newton, but in the case of ferro, it was only 25 picocoulomb per Newton. So high optical transmittance of the parallel capacitor ground crystal, higher mechanical stability of the ITC ground crystal, and higher crystalline perfection, which clearly indicate that the parallel electric capacitor ground crystal at high temperature, 54 degrees Celsius, will be more useful comparable to the crystal grown at its room temperature. So when we grow the crystal with solvent of water, there will be no issue. But when we select the acetone, ethanol, methanol kind of solvent, because of the fast evaporation rate, multinucleation will be formed at the bottom of the SR glass ampoule. In order to avoid these issues, we have introduced the glass bend. With this modification, we have grown almost all the crystals. So this is the 2-amino-4-nitrophenoid crystal for nonlinear optical application. This is the 4-nitrophenoid derivative single crystals. With the help of this modification, we have successfully grown and we use it for the SKG application. And for point seed rotation techniques, this is a schematic diagram. This is the actual seed crystal. We have selected the 001 direction, C direction for the longest growth. And this is the 2-liter solution container. This is the 5-liter solution container. So we optimize the cooling rate at 0.1 degrees Celsius per day, 0.2 and 0.5. When we maintain the temperature at 0.5 degrees Celsius, you see there will be a lot of microcracks that appeared in the crystal. Multinucleation will be also formed in the ground crystal. So this is the optimized cooling rate for this point seed rotation technique. So this much of large size crystal can be possible by this point seed rotation technique. From this point seed rotation technique, we have successfully fabricated the type 1, type 2 SKG element. From these 1-inch crystals, we have selected for the optical transmittance measurement. We have achieved the more than 90% optical transmittance for this 1-inch crystal. And we have fabricated the type 1, type 2 SKG element in RRK Tindu. And as mentioned in a conventional SR method, there are a lot of impurities are segregated. So there is no way to go out the impurities in the conventional SR method. In order to avoid this issue, we have made the several slats and holes in the RSR method. This is a schematic diagram of the RSR method with the slat, and this is the RSR method with the tube. So this is the RSR method with slat. This is the RSR method. We mount the seed crystal here. We apply we cool the temperature from high temperature to low temperature. The crystal will be grown like. So this much of large size transmitting crystal can be passed by this RSR method. So the impurities are pushed up from the glass sample. One can easily minimize the impurity segregation in the RSR method with glass and RSR method with the tube. So this is the different growth stages of this RSR method with the slat, and this is the RSR method with the tube. And this is the as grown crystal. This is the cut and polished wafers. So this is a crystal grown by the SEST method in a crystallizer. This is the crystal grown by the SR method. This is the crystal grown by the RSR method. In order to check the crystalline perfection of this SR, SEST, SR and RSR, we have carried out the HRXD measurement because of the lot of solvent inclusions, microcracks, milky opaques, and high dislocation density. The FWHM full width at half maximum of this SEST method grown crystal was 56.5 hours again. But in the case of SR method grown crystal, there is no solvent inclusions, microcracks, milky opaques, and morphological defined facet. The crystalline perfection is slightly increased from 56.5 to 45.5 hours again. But still, there are a lot of impurities are segregated in the conventional SR method. So we have introduced this RSR method. Here we have minimized the impurity segregation. So automatically the crystalline perfection is improved from 45.5 hours again to 30 hours again. So this is a simple comparison between the RSR and normal conventional SR method grown crystal. When you minimize the impurity segregation, you see the optical transmittance is increased and the mechanical stability also increased when we reduce the impurity segregation. And this is the comparison between the conventional SR method and the RSR method with the minimized impurity segregation, 12.5 gigawatts per centimeter square. But in the case of conventional SR method, it is 6.25 gigawatts per centimeter square. This is the immersible ample Sankaraya Ramasamy method. We simply pour the entire solution. We prepare the solution with high temperature like 50 degrees Celsius, and we reduce the temperature like 0.1 degrees Celsius per hour from 50 to room temperature, 32 degrees Celsius. The crystal will be grown like this. So this is the ISR method grown crystal inside the glass sample, and these are the cut and polished wafers to identify the homogeneity between the bottom, middle, and top portion. We have carried out the HRXD at its bottom, middle, and top. Almost all the portion is same. The crystalline perfection is very good between the bottom, middle, and top portion. So the final conclusion of my lecture is we have selected several semi-organic single crystals, technology in single crystals. Initially, we grow the crystal by this slow evaporation solution growth method. We grow a lot of seed crystal with high transparent, with well-defined morphology. Using the single crystal X-ray diffraction morphological measurement, we identify the direction, we select the highly efficient material, and we apply for the SR method growth, and we grow the crystal at its unidirectional and bulk size. Comparison between the SEST and SR method is when we grow the crystal by this SR method, it is a single and morphological defined facet. So like SEST method, there will be no gross vector and gross vector boundaries and reduced gross vector boundaries in the SR method, so that the physical properties and crystalline perfection of the conventional SR method is very high. Still, there are a lot of impurities are segregated in the conventional SR method. In order to reduce the impurity segregation in the conventional SR method, we have introduced this RSR method. There we completely rotate the experimental setup of this RSR method with the solution, with the seed crystal, with the growing crystal. so that one can easily minimize the impurity segregation in the RSR method. This we have confirmed with several characterization like to identify the crystalline perfection of this RSR method. We have carried out the HRI and chemical etching measurement. The RSR method ground crystal is having less FWHM, full width half maximum, and a single and very sharp peak, which clearly indicates that the RSR method ground crystals are having higher crystalline perfection comparable to the conventional SR and conventional SEST method ground crystal. The physical properties like optical transmittance, Vickers microhardness, dielectric permittivity, and the optical homogeneity also. At a radical condition, we have compared the RSR method with conventional SR and conventional SEST method. The RSR method grown crystals are having higher laser diameter threshold, higher optical transmittance, higher mechanical stability, and higher optical homogeneity comparable to the conventional SR and conventional method grown crystal. So the final conclusion is this RSR method, rotational Sankaraya Ramasamy method, is more suitable for the any kind of optical and SKG and frequency doubling application. So thank you very much for your kind attention. This is our group with our PhD scholars, our director and principal and president. So thank you very much. If any question, I am very happy to respond. Thank you very much.
So one question from the organizer side. You said this SR method is a conventional method. Any other advanced method which we have not used in Indian laboratories, which are used in foreign countries? Like,
sorry, can you please repeat the question, ma'am?
So, sir, this SR method, whatever we use in Indian laboratories, SR method and other methods, everything. Like, is there any advanced methods available in foreign countries, but what we have not used in our laboratories for reducing the defects and other disadvantages?
There are three different categories. One is crystal grown by solution, and crystal grown by melt, and crystal grown by the wafer technique. For solution, this is the best method, ma'am. Very, very simple and cheapest method. Within very small amount, we can easily construct this method.
It is cost effective.
SEST conventional method, comparable to the slow cooling method, comparable to the immersible Sankaraya Ramasamy method, immersible solution growth method, constant temperature bath with cryogenic, without cryogenic. This method is best, RSR method.
Okay. Okay, sir. Thank you, sir.
Melt growth and wafer growth is very different. I am talking about only the solution growth.
This method. Oh, thank you, sir. Over to Shiba, ma'am. Ma'am, questions.
Thank you, ma'am.
Questions in the chat box.
Sir, summarized 3 questions. So the first question, is there any other preparation methods MLO crystals?
Please
is there
repeat,
any other preparation methods for MLO crystals?
No, but to grow the crystal, preparation means you are talking about the synthesis and the solution preparation. So initially, this is the only method, ma'am. Usually, initially we grow the crystal by SEST method. We get the well-defined morphology, we identify the direction, and we mount the crystal at the bottom of the glass sample in the SR method. We grow the crystal in the bulk form using the SR method. As I mentioned, in the SR method, in the conventional SR method, there are a lot of impurities are segregated. In order to reduce the impurity segregation, we introduced this RSR method for the past 5 years. There is no separate techniques to prepare the solution. This is simple preparation. NLO material means you have to select the material, you have to dissolve in the solvent, you have to filter the solution, you got these supersaturated or saturated solution, you pour in the beaker or petri dish or crystallizer, so solvent evaporate, then you have to get the crystal. This will be the
next question. How long it will take to go crystal by SR method?
So it depends upon the solubility of your material. If it is a very low soluble materials, you have to wait very long time. If it is a very moderate soluble, if it is a very high soluble, you can grow the crystal within a week, within a 10 days, within a 2 weeks, you can get the crystal. Like that world's longest crystal, if you pour the solubility of the benzamide crystal with xylene is very high, 265 gram per 100 ml. So you just imagine, if we pour the solution in the evening time, you will get some crystals. So within a week, you can get the 10 centimeter longest benzone crystal. Depends upon the temperature what you apply at top of the glass sample.
Okay, sir. So the next question, how to measure birefringence of the crystal?
So birefringence, so you have to make it as a very thin plate like a seed crystal. We have that experimental setup in our laboratory, birefringence measurement. So just you measure the ordinary ray and the imaginary ray. You can simply measure the birefringence of your crystal. To make the optical transmittance, you have to get the very high thickness crystal, but birefringence, so you need only the 1 millimeter or less than 1 millimeter crystal you needed for the birefringence. It is very simple technique. You can easily measure our laboratory.
Thank you, sir, for the participant answer. And the final question, difference between type 1 and type 2 second harmonic generation materials. Difference between type 1 and type 2 second harmonic generation materials.
I think message irka ma'am. Can I read?
Yes, yes. Chat box. It is in the chat box. The last one, right? Yes.
So just for example, if it is a KDP crystal, potassium dihydrogen phosphate crystal, the phase matchable direction of this KDP is 59 degree. 59 degree. So the complete the crystal 360 degrees Celsius, you cannot use it for the practical device application. The 59 degree only useful for the practical device application. It is called as a phase matchable direction. Similarly, all the non-centrosymmetric crystals are having this kind of phase matching angle. So suppose TGS glycine phosphate, you cannot use it the entire portion for the practical device application. You have to identify the polar B direction using the single crystal X-ray diffraction morphological measurement. You have to identify, you have to cut, and you have to grow the large size single crystal along that particular direction, along the repeated direction. It is called as a phase matchable direction. For centrosymmetric, it will not there. It is not there. For non-centrosymmetric crystal, you have to identify using the measurement, and you got to grow the particular direction by this SR method. For all the non-centrosymmetric crystals are having this phase matchable direction, but it will vary from the material to material. So usually we compare the crystal with the KDP, potassium dihydrogen phosphate. For any kind of non-centrosymmetric crystal, this is the standard material for our crystal growers, KDP, potassium dihydrogen phosphate. When we measure the powder or single crystal SHG measurement, second harmonic generation, and we compare the direction between the KDP and our ground crystal.
Thank you, sir. Since there are no further questions, we can come to the first day of the activity. Over to Vila ma'am.
Thank you, Annie ma'am. Thank you, sir. It was very informative and very useful and simple explanation. We could understand this topic. Kindly, participants, can you switch on your video for a photograph, and then we'll move on to the word of thanks session. Participants, kindly switch on your videos for a photograph, for a picture, and then we'll move on to the word of thanks session. Yes, Chitra ma'am, is the photo over?
Yes, ma'am. It's more. Okay, thank you.
Thank you, all the participants. Now over to Annie ma'am for word of thanks.
We have shared a feedback link in the chat box. Participants are requested to fill it. On behalf of the organizing committee, it is my privilege and honor to deliver the vote of thanks at the end of today's enlightening session. First and foremost, I would like to extend our heartfelt gratitude to our resource person, Dr. Muthusendil Pandiyan, for accepting our invitation and sharing his deeper knowledge on the topic, physics of single crystals for technological applications. Thank you, sir, for sharing such valuable insights into the fascinating world of single crystals. Your remarkable depth of knowledge and experience in the field of single crystals growth techniques, starting from possible growth setups, stages of growth, cutting of single crystals, and applications. It is rare to witness such clarity and command over the single crystal growth techniques, from simple methods to higher end growth techniques. Session has been immensely beneficial, especially for our researchers and faculty members who are continuously exploring the frontiers of material science and development of advanced materials. Also, have opened up new perspectives for ongoing research and academic collaboration. Your passion and precision have greatly enriched our understanding and sparked new interest in the possibilities that lie within this field. Such knowledge and research experiences sharing sessions are available and invaluable in keeping our academic community aligned with cutting-edge developments. We are glad to have you with us today, sir. Once again, thank you, sir. Now, I would like to take this moment to express our sincere thanks to our NPSBCT management, founder and chairman K. Loganathan, Vice Chairman N. Naveen Prasad, Director Professor A. Saminathan, Principal Dr. T. Saranathan for the vision, constant support and encouragement to drive the academic spirit of our institution. We thank our head of the department, SNH, Dr. S. Sivagami, and our department faculty members for their unwavering support and facilitating this program. Our sincere and heartfelt thanks to all the participants. Your involvement and active engagement played a key role in making this activity a meaningful and successful experience. We truly appreciate everyone for your valuable time and commitment. Let us carry forward the momentum and continue to learn, share, and grow together. Once again, thank you all for making the first day of this activity a success. Have a wonderful day ahead.
Thank you. Thank you very much, madam.
Thank you, Sindhi sir.
Thank you, sir,
so
for
much.
joining us.
Thank you, madam. Thank you. Thank you. Thank you.
Thank you, participants. Now you can leave the meeting.